Hello everyone. Today I'll be discussing the next experiment that is a MathWorks example. This algorithm or this particular example is present in the MathWorks website. So we will be discussing that in detail. That is a dynamic rate control simulation in an IEEE 802.11 AC channel. So the learning objectives include to create a single user SU high throughput format configuration object and initialize the transmit parameters of 11AC standard. 11AC is also called as Wi-Fi 5, that is the predecessor of 11AX. 11AX, we know it is called as high efficiency. In short, it is called as HE. Likewise, 11AC standard is called as VHT, that is very high throughput. So here we configure TGAC channel of 40 megahertz bandwidth using a WLAN TGAC channel system object, which is there in the WLAN toolbox. Then we pass this transmit waveform through the TGAC channel and add AWGN to the transmit waveform. At the receiver, when we do receiver processing and do the SNR estimation, then select the MCS, that is a modulation and coding scheme based on the SNR estimate. So this is the block diagram of the dynamic rate control simulation. And again, this figure is taken from the MathWorks website. Here, what is done at the transmitter, we are generating a packet waveform using WLAN waveform generator. Then we model the channel characteristic using the WLAN system object called TGAC channel model. There we specify what is the do we need large scale feeding effects, or what is the transmit receive distance, what is the number of transmitters, receivers, there is a path loss enabled, etc. So here we do the channel settings. Then at the receiver, after the signal is being faded from the TGAC channel, we add the AWGN noise. And at the receiver end, again, you need to synchronize the packet and estimate the SNR. Then based on the SNR estimate, do the MCS selection. And this MCS is fed to the transmitter so that it selects the MCS, whatever the MCS selection or the MCS suggested by the receiver based on the SNR estimate. The suggestion is given to the transmitter so that this MCS would be used for the next packet, which is to be transmitted through the TGAC channel. The processing chain includes these number of steps. Again, this is taken from the MathWorks website. Initially, PSD is created and encoded to create a single packet waveform. And in the simulation, they assume a fixed idle time between successive packets. The waveform is passed through the evolving TGAC channel, and we know that WLAN channel is a slowly evolving or slow fading channel. AWGN is added to the transmitted waveform, and they make use of a function called process packet, wherein the transmitted waveform is passed through the TGX channel in order to model the channel effect on the transmit waveform. And it also performs the receiver processing and the SNR estimation, the same function process packet. Within this function, the main thing or most important signal processing is like VHT LTF is extracted. It is demodulated, and then channel estimation is performed using this VHT LTF field. And further data field is extracted from the synchronized receiver waveform. The noise estimation is also done using the demodulated data field pilot subcarriers. Then the estimated SNR for each packet is compared against a threshold. So they define something called threshold SNR vector. So whenever they estimate SNR for every packet, they are going to compare with the predefined SNR threshold vector and then select the MCS. We will see that in detail what exactly it means. Then the PSD is recovered at the receiver using the extracted VHT data field. And one more thing to note for simplicity, this example or this code assumes some of the things. First is assume fixed bandwidth and antenna configuration for each transmitted packet. And then there is no explicit feedback packet to inform the transmitter, okay, this is the MCS. As I told you earlier, MCS is estimated or MCS is chosen based on the estimated SNR at the receiver. And then this here it is assumed that there is no latency or feedback latency for the MCS feedback, or it assumes that the chosen MCS information is known to the transmitter before transmitting the subsequent packet. and they assume fixed ideal time of 0.5 milliseconds between each packet. So next we will see what the algorithm does. So as I told you, this particular program is available in the MathWorks example. I can show you that thing. Yeah. So this is that example, and I have provided the link in the slides. So here it explained in detail for every block. It tells like what is it. So we will go through this now. And coming back to the program. So the program starts from here. So this example basically shows the dynamic rate control by varying the modulation and coding scheme of successive packets, which is transmitted over the frequency selective 11AC channel. IEEE 802.1 standard does not specify the rate control algorithm. It does not define any standardized RCA for the WLAN channel. But the implementation of this rate control algorithm is left open to the WLAN device manufacturers. So this example, as we saw in the previous slide, that it uses a closed loop rate control scheme, whatever the MCS is recommended by the receiver for transmitting the next packet. It's calculated at the receiver, but it assumes it is available at the transmitter without any feedback latency. But in real-time system, what happens? This information would be conveyed through a control frame exchange. So the MCS is adjusted for each subsequent packet in response to the evolving channel condition. So now we will do the waveform configuration here. The VHT waveform is created using WLAN VHT config. So here this generates the VHT configuration packets. Here the bandwidth is set to 40 megahertz. The initial MCS is set to 1, that is QPSK, rate half. Then the payload length is set to 4096 bytes. The channel is configured next. So WTGAC channel, then delay profile is model D. The CISO scheme again, number of transmitting antenna equal to receiving antenna equal to 1. The transmit receive distance. Oh, sorry, this is, sorry for that. This is say 20 meters. And the random stream is MTAR with seed. So seed value is set to true, and these are enabled in order to compute the channel impulse response. So coming to the rate control algorithm parameters. So typically what happens, the rate control algorithm uses channel quality or the link performance metrics such as SNR or packet error rate for the rate selection. So here the example provided by the MathWorks, the rate control algorithm estimates the SNR of the received packet. So on reception, the estimated SNR is compared against a predefined threshold SNR threshold vector. If the SNR exceeds the predefined SNR threshold value, then a new MCS is selected for the transmission of next packet. So here two variables are defined, that is RCA attack and RCA release. This controls the sensitivity when the MCS is increasing. RCA release controls the sensitivity when the MCS is decreasing. Here, this is set to 1, this is set to 0. So in order to in order to control the smoothness of the rate transition, these values are set. So if you can see, RCA attack is set to 1, so that the increase in MCS is not happening very aggressively, or I can tell conservative increase in MCS. But RCA release is set to 0. We will see that this happens very aggressively. Whenever the MCS has to decrease, then this happens very aggressively. Then the threshold, this is the SNR threshold vector, what I defined earlier. Here they have defined some values, but this may not be true for all channel conditions or the number of packets. For this particular example, they have said, but they have not told in clear, like how did they get to choose this SNR threshold vector. So that is one open question. Maybe this works only for channel settings for this particular distance model D, but this may not work for all possible cases. And here SNR up they have defined. Here basically what they're doing is they're taking the threshold vector and adding an infinity at the end, and also adding 1. So SNR threshold was from 11 to 35, but now SNR up is for each and every value in the threshold vector, they have added 1, and at the end they have appended by infinity. SNR down, what they have done, they have started with minus infinity and threshold and minus RCA release, but because RCA release is 0, I mean the threshold vector is unchanged. So if you compare threshold and SNR down, simply you have minus infinity at the beginning and the threshold vector remains same. There's minus infinity, 11, 14 and up to 35. Then they have defined a variable called SNR in. That is a index. They are referring to index index to access particular SNR value from the threshold vector. They have initialized to GVHT MCS, which was set to 1. Yeah, initially they have set it to 1, and the same thing they have initialized. Then yeah, the number of packets simulated is 2. Then something different is like walk SNR. So this is a variable. So if this walk SNR is set to true, what happens? They're defining again mean SNR, which is 22 dB, and amplitude is 14 dB, to generate varying SNR values for each transmitted packet. So the variation in SNR will be around the average mean SNR value, that is 14 dB. Again, base SNR is defined as sine of something, star amplitude plus mean SNR. So what is this? This is on this sine of this is computed every time. So what does line space do? Line space, first variable and second variable, common number of packets. Number of packets we have set it to 2000. So it basically line space, what it does, it will take starting from 1 to 10. It will create 2000 points in between. So the step size between each point will be same. So starting point will be 1, ending point will be 10. So it creates 2000 points in between the start and end points. So then sine of each of thing is computed. This is basically sine curve. Then each of the values multiplied by the amplitude, and then this mean SNR of 14 is added. So if you want to see how it looks, let me. This is something. So this was not there in the mathwork example. If you want to know what exactly it is, you might have understood the equation, but just want to make a sense of like how exactly it looks. You can just create a new figure and plot whatever your variable you're interested in. So as I told you, this is sinusoidal. This basically sine of line space. This also you can plot and see. It varies from -1 to +1. So since the amplitude is set to 22, mean is 14. So 22 into 1 plus 14, 36. So 36 is a peak value of the sine curve. And this is -1 minimum value. So -14 plus 22 is 8. So the minimal value for this will be 8. So this is a curve varying from 8 to 36. You'll find somewhere here peak value is 36. It is 36. So that we have seen. So now SNR walk, they are simply taking the first value from this function, okay, setting the initial value. Then max jump, they have defined and set it as 0.5. This controls the maximum SNR difference between from one packet to the next packet. That we will see like how it is being used. So they have set it to 0.5 now. And this happens whenever the walk SNR is set true. If walk SNR is set to false, simply SNR walk is 22. So they are fixing the mean SNR value. So and all the variability comes from the time varying radio channel. So if the SNR walk is 22. So to repeat, so in this simulation, the number of packets are transmitted is 2K. The channel state is maintained throughout the simulation. Therefore, the channel evolves slowly over the time. So this evolution slowly changes the resulting SNR, which is measured at the receiver. Since the TGAC channel changes slowly, here the SNR variation at the receiver is visible only over a short simulation. So this can be forced by using a walk SNR parameter in order to modify the noise power. So here setting this walk SNR to true, what happens? The it generates a varying SNR by randomly setting the noise power per packet during transmission. So when doing all these, what happens? The SNR walks between 8 to 36 dB using this amplitude and mean SNR variation. Oh, that is how we will see, because base SNR again it is used here. Actually, base SNR has 2000 samples in it. To initialize with, it has taken SNR has taken as a first value. So setting walk SNR to false, as I told, simply what happens? Simply the SNR walk is set to 22 dB, which is fixing the noise power to all the samples of the received waveform, and the channel variations becomes the main source of SNR change at the receiver. So if you fix it, the noise power is not varying for every packet. But here in this case, if SNR is true, you're trying to vary the noise power for every packet which is being later used at the receiver end. We will see that. So this is the selection of SNR for the simulation, basically to model the noise power which is being added after the transmit waveform is faded by the 11 AC channel. Again, if to plot the equalized constellation, you can make use of this. As of now, it is set to false, but you can set it to true and see how the constellation varies for every packet, because MCS change accordingly, the constellation diagram also varies, changes for every packet. So here they're initializing, then are measured. This is something which is to be computed. So since I've already run the code, it's already computed what is the SNR for each packet. Again, MCS is initialized to 0, so that because in the beginning we don't know what is the MCS, so initialized to 0 to BR. BR, this tells whether the packet has successfully received, decoded at the receiver or not. So this is also initialized to 0. The packet length is the time taken for the packet in seconds or milliseconds. So this is also set to 0. This is required so that it is required to compute the throughput. So packet length is required. So initially it is set to 0, and the length of each of these variables is set to packets, that is 2000. Then the processing chain, as I told you, PSD is created, encoded. You can go through these points later, but I would like to explain the same thing through the code. So let's go further. Yeah, so here if you see, this following steps is done for each and every packet. For packet equal to 1 to num packets means for each and every packet, this processing happens. The following lines of code are executed for every packet. So if walk SNR, yes, we had enabled walk SNR to true. So now base SNR of num packet. So this is being used. For initialize, simply they had taken base SNR of 1, if you remember. Yeah. But base SNR is a vector of 2000 samples because we have used line space and num packets, which is 2000. So they are creating a vector, or not vector exactly, because for every packet this gets executed. So SNR walk is simply a scalar quantity, but this changes for every packet. That is because two things: base SNR of num packet changes for every packet. And then we're also using a rand function. So rand function is generating a random variable in the uniform distribution between an interval 0 to 1. They are multiplying my max jump. So max jump, I told this is used and it is set to 0.5, and they told it controls the maximum SNR difference between one packet to the next packet. So that is a max jump. So here when you go to this particular line, this varies according to that equation. So this base SNR of num packet is different for different packet. So random one also varies, where that takes a value between open interval 0 to 1. Max jump is 0.5. Say go to the extreme case where random is 0. In that case, what happens? The complete term. Okay. The random 1 max jump into 2 minus max jump. What happens? When random approaches to 0, this particular term approaches to minus max jump. Okay, that is minus 0.5. When random approaches 1, the whole term approaches plus max jump, that is plus 0.5. Say if random is 0.5, okay, then this complete term approaches 0. So that is what they're telling. So they have used max jump in such a way that the maximum difference between SNR difference between this is set to 0.5. where was that maximum? The maximum controls the maximum SNR difference between one packet to the next packet. Okay, this is for modeling the the noise part. Okay. Okay, so now coming to this thing again, TXBSD, what it does, it randomly generates the bits based on the length that we have set it to 4000 something. Then TXWave creates the waveform, which is of size NS cross NR. NR is 1 here, NS is the number of samples. 5 milliseconds, they have assumed idle time, that is between packet to packet. And then this TX wave, the SNR walk for that particular packet, it's a scalar, TJAC channel, the configuration object for VHT, the num packet. Num packet is the index telling what is the current packet. And num packets is the total number of packets. Since our code is already executed here, num packet is equal to num packets, total number of packets. But otherwise, num packet takes the value 1, 2, 3 like that. So everything is passed to the process packet. This basically does the receiver processing. Coming to this code, so what it does, it initializes again to an empty array because these are the variables which needs to be estimated for every packet. So this is initialized to empty vector or a null vector. This is because it shouldn't overwrite. So one packet for this packet, it computes. And when next packet initialized again to null vector, again it computes every time. So that's why it is initialized to empty array. So your DAM info can be obtained. Then this waveform is passed through the fading channel, right? And yes, as I told, reset is not used. You can see what happens reset is used. And this RX wave is now is a faded signal. So this is something which I have done extra. This was not there in the example code. Simply I'm trying to see what is the channel impulse response after 1/4 of packets, 1/4 of packet, that is after 500 packets, after 1000 packets, and after 2000 packets. I'm simply sketching impulse response and comparing. That's it. This was not there. This was not there in the example code. So here you're creating the AWGN channel using the communication system object, that is com.awgn channel, and they have set the type to SNR, and they make use of that SNR walk, which varies for different packet in order to compute the AWGN SNR. So this RX wave, earlier it was faded because it was passed through TJS channel. Now the same RX wave they are taking and it's passing through the AWGN channel system object. So this thing, whatever you have got, this RX wave is different from this RX wave because this RX wave within the argument was only faded. Now the LHS RX wave is faded signal. Noise also is being added to the signal. Okay, fine. So I am seeing what is the waveform length. Obviously, this how it should be equal to the transmit waveform length, right? Because simply you're adding the noise. Okay. So I have something to comment here. Here in this example, what they are doing, they are generating this SNR walk they have used, and using that they are generating noise using basically the noise sample, whatever they have generated, it is different for different packet. In practice, we don't model AWGN like that. AWGN is like additive white Gaussian noise. So in practice, what is done? You simply create a complex Gaussian noise vector. For example, n is equal to x plus jy, right? Where x is Gaussian, y is Gaussian. Then you will have something noise which is complex Gaussian noise samples. But how to generate? Say you can set the noise power around -90 dBm or -120 dB watts. Then compute the noise power, that is Pn. When it is -120 dB watts, what is Pn? Pn is 10 to the power -12 watts. Okay. So then from this obtain the noise power. Okay. Noise power, that is sigma. Then you will generate the noise samples as x plus jy, where you compute x is obtained from rand of 1, rand n of 1, and y is also obtained from rand n of 1. The whole thing is multiplied by sigma as a noise power. this is a better way of obtaining the noise samples. Then how many such noise samples has to be obtained? That equal to the length of the received waveform or transmit waveform. And then all these noise samples is added to the RX waveform. For example, here RX waveform length is let me see what is RX waveform length. Yeah, because within the function there was a line which I executed, so MATLAB is not able to recognize the variable. But yes, this TX wave is lying outside the process packet function. So it is 70,240 samples. You need to generate such so many samples, but with fixed noise power, then you can add. That is more better way of approach. But in this example, somehow they have used this SNR walk and they're telling they're varying the noise samples for every packet. Okay, but in practice, better approach is fix the noise power, say 10 power minus 12 is minus 120 dB watts. Obtain the noise variance, right? Or sigma. Sigma standard deviation sigma is what under root Pn by 2. Then how do you generate noise sample? The noise sample is equal to sigma, whichever you have computed, whatever you have computed from Pn, multiplied by random of L comma 1 plus J random of L comma 1. So here L tells the number of samples, or yeah, the number of samples in the TXMU wave. Then you have noise samples, which is equal to the number of the TXMU wave samples or equal to the number of RXMU wave samples. Simply do RX wave as, instead of this, what you can do is simply do RX wave as TGAC channel of TXMU wave. So this thing, TGAC channel of TX wave, this is after fading. To this, if you add noise samples, which is equal to the length of the TX wave, you will get the RX wave. There's one more approach and it's a better approach, but I'm just trying to understand or explain whatever is the example code. So in this, one thing to note, you should noise is varying for every packet. Okay, fine. After that, at the receiver end, in order to recover, they are trying to get the different fields of CFG VHT. This int will have different fields. Then first and foremost step is packet detection. So WLAN packet detect, there is a function WLAN packet detect. RX wave is passed to that, and packet offset is computed using WLAN packet detect. So this is just the packet detection using LSTF. So we have seen the packet preamble in the experiment 3. So LSTF, LLTF, and LSIC, they are the legacy part, meaning even the standards earlier to the 11AX standard will have these three fields for the backward compatibility. So the first field is LSTF followed by LLTF. So LSTF field is used for packet detection. So if you can see what is WLAN packet detect, you can open, you can, whenever you don't want to see what is the function doing, simply right click and do open. So you will have WLAN packet detect, it returns the offset from the start of the input waveform to the start of the detected preamble using the autocorrelation. So here the X is what? RX wave, right? So this is the received time domain signal of NS, that is the number of time domain samples, and you will send and you'll also give channel bandwidth as the input parameter. So this gives the packet offset. It returns the offset from the start of the input waveform to the start of the detected preamble using the autocorrelation. And here this particular function supports only OFDM modulation. And this value can take, it's a scalar value, it can take 0 or greater than 0. 0 meaning there is no packet detected. And if it takes a value, it may take a value greater than 0. So that gives by how much amount the packet is offset. In order to understand this, the simple code we have here. So let's try to execute this and see. Basically, what is it doing? So create a non-HTTP configuration object, waveform is generated. Purposefully, they are delaying the signal by adding zeros, and they're using the WLAN packet detect to tell what is the start offset. So ideally speaking, because they have added zeros here, and start offset should give 0, because The packet detect is happening using the LSTF field. So receiver knows what is the LSTF. See this LSTF, LLTF, all these are like standard defines it. Basically, it will be generally BPSK modulated signal. Since the receiver knows what is the standard format for that, using that it does autocorrelation function and gives the value. So if you see here, packet start offset is 20. So this will validate whether this double LAN packet is working correctly. Since we introduced purposely 20 zeros, it is telling yes, packet start offset is 20. And going to the next thing, if packet is detected, if packet offset is 0, it means packet is not detected, it will throw error. If it is not empty, yes, packet is detected. Then what it does, for fine timing synchronization, it will again use this RX wave. So we know packet offset is something which is greater than 0. Okay, you can check what is the value in this particular code. In this example code was about 20, but here it may differ. So and this is done for every packet, remember. So for that RX wave, packet offset, whatever is the detected packet offset, estimated packet offset, that value is given, and then the LSTF is obtained. I mean the LTF samples are obtained. Okay, so meaning what, you in the RX wave initial samples may be noisy, that does not correspond to LSTF. Hence packet offset. Say for example, packet offset is 10. Then you are extracting only that portion of the received waveform which corresponds to STF after packet detection. This for that you need to estimate packet offset. So if packet offset is 10, meaning what, from the RX wave you are considering after 10 samples. So you're ignoring the first 10 samples. So packet offset plus the indices corresponding to LSTF. So you're ignoring the first few samples and then storing it in LLTF search buffer. Then this particular thing after ignoring the initial few samples, this you are sending to double LAN simple timing offset. So what is double LAN simple timing offset? Again, you can open and see what it does. So this does define simple timing estimation using the LLTF. So how does it do? It does the cross correlation. So before going to that, we'll try to understand what is a simple timing offset or simple timing recovery and why it is required. So simple timing recovery is also called a simple timing synchronization or the clock recovery. Okay. So, you know, at the receiver, the received analog signal, just there is first front end processing ADC happens, right? Analog to digital conversion. It samples the incoming continuous waveform without any information, without knowing information about the symbol boundaries. But for digital processing, the starting point of the useful component in the sampled signal must be known, right? Because most of the initial samples are noisy. So in order to obtain the symbol boundaries, the frame synchronization has to determine the symbol number in the received sequence. Once frame synchronization is achieved, the timing synchronization block establishes the optimal sampling instant with the symbol. So if you do sampling at the optimal sampling instant, there is no ISI from the neighboring symbols. If you have learned the communication, you know the eye diagram is wide open. Whenever you do the sampling at that optimal point, there is no ISI from the neighboring symbols. But there will be some phase or timing offset because the receiver clock is misaligned to the reference TX clock. So you need to extract the TX clock from the noisy receiver data itself, right? So that is why it's very important to do the simple timing estimate. Otherwise, if the signal is not sampled at the optimal sampling instant, the signal, there is huge ISI between the symbols. So what does simple timing offset do? Simple timing offset, again, it takes a signal and returns the offset from the start of the input waveform to the estimated start of LSTF using the cross correlation with LLTF. So packet detection was doing autocorrelation. So LSTF was autocorrelated with itself, but here for simple timing, it does the cross correlation, and the value, whatever it gives, will lie between minus L to NS minus 2L, when NS is the number of samples in the received waveform. So going back to this, so this has some number of samples, so we'll call it as NS. And capital L is the length of the LSTF. Again, that's a standard defined and it is fixed. So this value will lie between minus L to NS minus 2L. And this value, see if it is 0, then it means NS is less than NL. So the number of samples is less than L. And if the start offset is negative, it also indicates that input waveform does not contain a complete LSTF. So for this to function, the X should contain LLTF, right? If it does not contain, it has insufficient number of samples, then the packet synchronization or symbol time recovery does not happen properly. So once it finds the fine packet offset, for that again to understand better, you can execute some small codes to see how symbol timing happens. So here the signal is faded, AWGN is added. So here packet detection happens, it has got some offset. Again, this start offset is considered so that you ignore so many number of samples in the received waveform. Then again, you use symbol timing offset, you get and one more offset, right? There are two offsets now. This is obtained using cross correlation between LSTF and LLTF. When you further process, you need to consider both. So determine the final packet offset by, this is obtained by autocorrelation of LSTF. This is obtained by cross correlation of LSTF with LLTF. So you add them both to find the final packet offset. If the final packet offset is less than 15, meaning synchronization is successful, so you store the LLTF portion of it from the received waveform, use that final packet offset, and indices of VHT LTF, go to that corresponding samples and store. So this has now LTF. So now you need to demodulate this, right? For that, there is WLAN VHLT demodulate. So use that function in order to get the demodulated VHT LTF, right? So here, we know at the modulation is like OFT type. At the transmitting end, you would have performed IFFT, correct? So you need to demodulate. And when you do IFFT, it's like you have transmitted the time domain signal. At the receiver end, you need to do FFT in order to get back the frequency domain signal, right? So whatever the output of demodulate, that is the frequency domain signal corresponding to VHT LTF. Right, again, we have seen in the experiment 3, the LTF is BPSK and it is standard defined. It takes either +1 or -1. At the transmitting end, IFFT is performed, you get the complex samples, right? Then it is transmitted, fading happens, noise is added. At the receiver end, you need to do FFT on that. And when you do FFT, it is something like you are recovering the original BPSK constellation symbols. So ideally speaking, this has to be same as the transmitted one, but because of the fading and religion, that is an estimate. The demodulated thing will be same as that of the original BPSK signal. Okay. So this thing is again given to WLAN HTLDF channel estimate function. So this is something like now the pilot symbols, right? So y is equal to hx plus n. If you want know what is channel estimate h, what do? You simply do y by x. So y by x gives h plus n tilde, right? Or yeah, h hat plus n tilde. So this gives the channel estimate of the, so you're computing the channel estimation using the VHLTF. Then there is one more function which computes the channel estimates on the pilot subcarrier location of VHT LTF field. You can open and read this and for further information. Then you extract the data field, VHT data field. Everywhere, if you note, you have used the packet offsets in order to ignore the initial noisy samples. Then you're going to estimate the noise power in the VHT data field using the VHT data. So you get the noise variance estimate. Then you do the data recovery in order to get the XPSTU. So this VHT LTF, you do compute the SNR estimation using VHT LTF. So VHT LTF is, after using packet offset, you would have obtained the VHT LTF, right? So using that, you compute the power. This includes signal power as well as the noise power, right? It's called channel power. So from that, you subtract the noise power. So signal power plus noise power is first term. When you subtract noise power, what happens? You will have only signal power. So that you're going to divide by the noise power in order to get the SNR. So the first term includes signal power plus noise power. Here you are subtracting noise power estimated with estimated variance, so that we have estimated signal power. Now to compute the SNR, subdivide estimated signal power with the noise power. So have the estimated SNR. So this function returns RxPSTU. RxPSTU, this is in bits. Right? After data recovery, you have RxPSTU in bits. And also the equalized data symbols, waveform length, noise variance, estimated SNR. So everything is returned as an output parameter. Once you get these variables, what is done? Compare whether the SNR measured is empty. If it is empty, you store that as nan, not a number. Yes, whatever the estimated SNR is sent by the process packet, stored in SNR measured. So it is a array. So every packet you're going to store it for further use. You're also computing already the received the received waveform length divided by the sample rate gives a packet length, right? So that is stored. This gives a packet length in seconds, including the idle line. Then you calculate the PER. Okay, if this RxPSDU, if it is empty, again you set PER as none. If not, if RxPSDU is non-empty, what do? You compare error twice the RxPSDU and TxPSDU. If you do this, there is a bit error, which is a function. It accepts two binary representation. So this X and Y are binary. This it compares X and Y. This number gives a number of differences in the binary representation. Say if you have X vector, Y vector, it's binary, ones and zeros. If there is two bits are different, then number will have two. Say length is 10, X is 10 element, Y is 10 element, then the ratio will be 0.2. So this is it gives the number of differences in the binary representation, which is output in the number, and the ratio gives the number to the total number of bits used in the binary representation. So coming back to this, now the second, this will have the BR every packet. Okay, so it is stored in the num packet. So BR is a vector. You will have BR computed for every packet. Then here, for the current packet, initially you have set to 1, right? So this for the current packet, you store it in MCS num packet. Now let's see this. This goes for the MCS for the next packet. So the current packet MCS is stored. Two variables is defined. Increase MCS, decrease MCS. Basically, here they're comparing with this estimated SNR with the estimated SNR with the that SNR threshold vector we had already defined, right? If the SNR vector they are compared, and whenever the estimated SNR is trying to see where exactly it lies. So this is a threshold vector. If it lies somewhere between, the estimated SNR is 24.6, then the MCS suggestion is 4. Because if it is less than 11, MCS suggestion is 1. Or okay, SNR up divided by 1. So if you say SNR up, it will be 12, 15, 19, up to 36, right? So if it falls below 12, then MCS suggestion is 0. If it falls somewhere here, 1, 2, 3, 4, something like that. So if MCS is 24.6, MCS suggestion is 4. If it is 23.5, again it is 4. Say if it is 27.2, then MCS will be 5. So they based on the threshold vector and this RCA increase, there were two variables, right? To see how fast the MCS change happens. RCA attack, yeah. So RCA release values. What it does, it compares estimated SNR and see which MCS has to be chosen. So this is a simple thing. You initially MCS is set to 1. Gradually it increases. For the second packet, it does not abruptly change to 5. Say, even though the SNR is 25 or 26, it does not abruptly change MCS to 4 or 5. It will change. MCS becomes 1, then 1, 2, 3, 4. MCS initial number of packets, MCS increments happens only by 1. For that, this is very important. Increase MCS, decrease MCS. If increase MCS is 1 and decrease MCS is 0, then MCS increases by 1. If both are 0, then MCS remains same. So it takes few number of packets in order to choose optimal MCS. But once it locks to the optimal MCS, then the change or the variation in the SNR appropriately chooses MCS. Then that particular MCS chosen is stored so that this can be used for next packet. It is stored in vht.mcs, and we know the MCS chosen this is the configuration object. This configuration object holds the MCS value, so they're accessing that particular property and storing the MCS value there. Initially, it was initial 1. Okay, so receiver processing is done. And ultimately, they want to plot. For plotting, it is simple. They compute overall data rate, overall packet error rate. For data rate, what they have done, this is the length in bytes. So they convert it multiplied by 8 to convert it into bits. This gives the number of successfully received packets, so the number of packets which are successfully decoded in the receiver. A num packet is a number, that is 2000. So num length of find of BR. BR, we know, it will have, it's a vector of packets. If it is 0, it means the packet is successfully decoded. If it is non-zero, meaning packet is not successfully decoded at the receiver. Find BR will give the index points at which the BR vector is non-zero. Okay, we are not interested in the index points. We are interested how many number of packets were not successfully decoded. So for that, we use num length. So num length of find of BR basically gives the number of non-zero values in the BR vector. Okay, that corresponds to the number of packets that were not successfully decoded at the receiver. So total minus number of failed gives number of successful packets. So this thing gives the number of successful packets divided by sum of packet length. I told you packet length holds the duration, the time period required for the transmission of each packet. Again, packet length is a vector. You want to add everything. It gives what is the total time taken in order to process 1000 packets. So this bits divided by this. Again, they have divided by 1 exponential 6 in order to express the throughput in Mbps. Okay. Overall packet rate, again, simple. Num length of find BR gives a number of packets which are not successfully decoded or which are in error. That divided by total number of packets gives overall packet error. Okay, when you for the complete simulation run. So for plot results, they're calling one more function, plot results. Here MCS, they have chosen MCS now holds a vector which has the MCS for every packet they're plotting. They've used subplot. So packet number, plotting MCS. Second, SNR measured stored, right? The particular Y process function was computing, process packet function was computing estimated SNR. It was estimating SNR. So that is stored in SNR measured vector and that is plotted. And this is something which is what they have done is they are trying to plot BR for every packet. I told find BR not equal to 0 means find gives the index points basically. Whenever BR is not equal to 0, meaning whenever BR is equal to 0, meaning the packet was successfully transmitted. So here that they are showing, and whenever BR is greater than 0, meaning they're not successful, again that is plotted, and they are tagging as successful decode. The X corresponds to successful, and O corresponds to O in red, in corresponds to unsuccessful decode. Coming to the throughput plot, they have defined some window length. Here they are computing the moving sum average. So again, this is the number of data payload length in bytes, 8, and here they are considering only what the successful packets, and they are computing the using the average window length. They have set it to 3. You can what sum does. You can do help move sum, do some examples. It's basically what it does. If window length is 1, it does not change. Move sum doesn't do anything. If window length is 2, basically it adds every 2 elements. Say 1, 2, 3, 4 is the input vector. Then move sum, what it does, move sum of that vector 2 simply takes 1 plus 2 is 3, 3 plus 2 is like that. So why is this done? So that the throughput plot is not very doesn't look ugly. So it just smoothened the throughput plot for appearance sake. This is just for plotting sake. They've smoothened the throughput values. So again, title, this is a throughput over last 3 packets. For every point, when you look in the curve, the curve here, this throughput plot, every point here corresponds to the throughput of number of data bits successfully recovered over the duration of 3 packets. Last immediate previously three previous packets. So this is, as I told you, I'm just plotting the impulse response in between. So this is the MCS which is plotted. So you can see MCS is varying whenever the estimate, whenever the SNR is good, the channel is good, MCS is good. Whenever the SNR is poor, MCS is 0, but SNR is so bad here, even if the robust BPSK is transmitted, still it's going error. So this particular is error. Okay. Again, when SNR improves, MCS improved. Whenever SNR falls, MCS is stable. So the MCS is following the SNR. MCS is increased whenever SNR is increased. Whenever a channel is good, here SNR is bad, therefore you see BER. I mean, this particular packet is unsuccessfully loaded. Again, if you throughput depends upon the channel condition, when SNR is poor, the throughput is poor here. Throughput is expressed in Mbps. I think that's all for this particular experiment. So in detail, everything is given in this. You can just go through. I have tried to explain each and every function here. If you want to read more on that, please open function and read. There are also some examples to be given so that you understand it better. And I wanted to show one particular textbook here. Yeah, this is the next generation wireless LANs, 11N and AC, given by Pereira and